Bismillahirrahmanirrahim. Lecture 05 Electronic Devices and Circuits, in continuation with the diode, but this time we will study about the properties, about the characteristics of a diode. So the properties and the characteristic we will study using the numerical examples, by having its characteristic curve drawn, and then we will describe about its properties. So before going to this, the diode characteristic or the diode properties can be divided into three parts. Number one is the ideal diode. Number second will be the approximate diode, and the third will be the practical diode. So we will study all these three all we will study the diode properties characteristic under all these three categories. Okay, so first we will describe about the diode, and first we will describe about the ideal diode. Okay, then the approximate diode, and then the practical diode. So we will see the difference. It's easy lecture, and hopefully you will not have any complicated part here. So yes, the ideal characteristic of a power device, it's for every device. If you design a machine, if you design a device, if you design a sensor, or whatever you design, you should have in your mind that okay, this device should have this property, and that is known as the ideal property. Okay, so we will always try to chase the ideal property. So now we are designing the PN junction. No, sorry, we are designing the diode by making a PN junction. So we did in the previous lectures. So we will see how much this diode, this our design, this diode is close to the ideal property. So in order to know this, we should first know what are the ideal properties. We should have distinct and clear understanding of what is the ideal diode. And if we know then we can list the ideal property of a diode. So we will try here to list the ideal property of a diode. So here the first property is okay. An ideal diode means a perfect PN junction. That's right. We know that the PN junction is basically a diode. Okay. So an ideal diode means a perfect PN junction. What is the perfect PN junction? We know about. I just give an example. For example, the PN junction has potential barrier. It's a barrier voltage is 0.7 for silicon. So we should, in order to turn on the PN junction of the diode, we must have to first overcome this barrier voltage. Means the external supply voltage must be greater than 0.7 volt. Then it will turn on. Okay. So this is the actual property, and what we need ideally the diode should be like this. If it should not have any barrier voltage, it should not have any potential any yes any it should not need external potential to turn it on. What should the ideal, what we assume that the ideal should be for, if it should be a silicon device. A silicon device, it has two terminals, anode and cathode. Whenever we connect the supply to the anode and the cathode, it should turn on. It should not have barrier potential of 0.7. It should turn on as soon as we turn on the external power supply. So these are, hopefully you will try to understand the ideal and the actual property. So an ideal diode means perfect PN junction. What should, we can also say a diode simply. Ideally we should design a diode, and this diode should have ideal property. Whenever we connect an external supply, it should turn on. Whenever we remove the external supply, it should turn off. But this is not in actual case. We know that if we must have to give uh, 0.7 volt in additional, so the extra 0.7 volt we need to break the barrier of the. So this what we need in the ideal, that it should not need any additional voltage to break its barrier voltage, or it should not have barrier voltage. The ideal diode is this. I'm just trying to explain more and more because you should have a very clear understanding, and it is this knowledge of the ideal property of a diode is will not only limit to the diode, but whenever you will study the Zener diode, whenever you will study the other diodes, or the semiconductor transistors, or the MOSFETs, or whatever the SCRs, or the TRIAC, or whatever device you will learn, you should have always a clear understanding of that is the what what should be its ideal property. For example, transistor, what should be its ideal property, what should be its approximate, or what should be its practical property. So that's why I'm spending a lot of time. So hopefully you understand. Okay, so what is here? An ideal diode means a perfect PN junction. Hmm. Okay, the ideal diode means diode we are looking should have the most desirable property that are most convenient to us. So ideal means it is our desire. It is we need we need such type of device that should be convenient, most convenient to us. Okay, so this is okay. Now for example, if the diodes are turned off or on, its property should be equal to the property of a simple electrical switches. What simple? Yes, I forgot to tell you. The diode is if we try to put the example of a diode, it's a mechanical switch. For example, here this is the piano switch, and we turn this diode off, there will be no flow of current. Similarly, the same property should be for the diode. When the diode is not externally connected, it should not have any flow of current, and the same is for this one. And whenever if we turn this switch, piano switch, turn on, then what should happen? It should immediately allow the flow of the current through the loop. And same we expect from the diode whenever the diode is forward bias, or whenever the diode is externally connected with a positive supply to the anode, then it should immediately turn on. So there could be one more example of mechanical switches. So the diode, we can understand diode by taking the example of a mechanical switch, because we all are familiar with this one. We should take one more example of mechanical switch. This is also mechanical switch, but normally this is knife mechanical switch. Select so it needs mechanical power to turn it on. Whenever we push this lever down to make the perfect contact, then this will become a switch, and the switch will turn on, and the flow of the current is possible. Whenever the lever is pulled up, then the connection is disconnected. There is no connection, so the current will be zero. So again, for example, if the diodes are turned off or on, its property should be equal to the property of a simple electrical switches. If the diode is on, or if any of the switch is on, the current will flow. Same is true for the diode. If the diode is off, or both of this, or any or both of the switches is off, then means there should be no flow of current. These are the ideal properties. So we can correlate the property of the diode the with the commonly available switches. We are quite familiar with these switches. Okay, so we have diode here, the anode, and cathode. In order to turn it on, we need to connect external supply, plus supply to the anode, and the minus supply with it. Okay, let's see. Okay, this is the example. I think this we are showing an example when the diode is off. There is no external power. If the diode is off, it means mechanically the switch is off, and there should switches like this one, and there should not be flow of current. So if the diode is this one, and if this diode we assume it's off, then it can be written ideally with this picture that diode is off, anode and cathode. So this one is completely off, so there will be no flow of current. Okay. And when number four, when off means diode is off, it exhibits high voltage drop, infinite resistance. That is, it blocks any flow of current during the off position. This sentence you have to understand. You have to pay some attention here. So if the diode is off, it means what is the resistance from here to here? It is an open circuit. Resistance will be infinite, very high, very very high. Okay, so when the diode is off, the one property is that if this is off, its one property is that its resistance from anode to cathode is resistance from anode to cathode should be very very high, or we can say it should be infinite. Number one property. And the second property is, because yes, this is completely disconnected, diode is disconnected, then there should be zero flow of current. The second property is, if the diode is off, the current from anode to cathode is zero. We can say it cannot allow the flow of the current. Similarly, with this one. Now, the third property is, so anode and cathode, what will be the voltage at anode and cathode? Whatever we connect the external supply at anode and at cathode, that will be the voltage across the anode and cathode, because the anode is connected. We are assuming that the anode is connected with the external power supply, and cathode is also connected with the external. So whatever be the external power supply voltage, that voltage will appear across anode and cathode. So there are three properties we learned here. If the diode is off, the resistance from anode to cathode will be infinite. Number two, the current through the anode and cathode will be zero. And number third, the voltage at anode and cathode will be the connected supply voltage. That is, the voltage will be the maximum. Okay. So when off, it exhibits high voltage drop. Means whatever the supply voltage, that will have the voltage at the anode and cathode. Infinite resistance. Yes, this is an open circuit. It's infinite resistance. That is, it blocks any flow of current during the off position. So the flow of the current will be zero. Hope you understand this one. And if we draw the, we are studying about the off status, and if we draw the voltage and current characteristic of this ideal diode, so what is the, we know that the for this ideal diode, the current is zero. So we can say the current is zero. There is no current is zero. And whatever be the voltage will be the supply voltage, anode and cathode. So the voltage will be maximum. So this curve represents the off status of an ideal diode. Remember this, we are studying the ideal diode. Later on we will study some more practical diode. So this is the status for the diode when it's for an ideal diode, when this ideal diode is in the off status. Now we move to the on status. Again, take the same diode, and we are assuming that this diode is on. Why it is on? Because the supply is connected here and here with the external supply, and we are assuming that this is on. If this is on, like this one or like this one, if this is on, means that the lever is pushed down, and it becomes a conductor, so it can allow the flow of the maximum current. So if the diode and what more, if this is down, it means these 2 points are is connected with this conductor, with this knife. So it's a conductor. So if the diode is on, ideally what we can say, it is completely short circuit. There is no barrier voltage, there is nothing. So if the diode is on, and for an ideal diode, we assume that anode to cathode there will be a complete conductor as for this one. And if this is a copper wire, this is a complete conductor, what will be the resistance at anode and cathode? There will be no resistance. We are assuming that this is a pure conductor. So the resistance will be zero from anode to, ideally, if the diode is on, and then ideally the resistance from anode to cathode should be zero. And what more, if this is zero, if the resistance is zero, it means it can have it will allow the maximum flow of current. So whatever the power is connected with this anode and cathode, so it will allow the maximum flow of the current because this is short circuited. So two property we studied: if the diode is in the off status, the resistance from anode to cathode will be zero, and if it is zero, then maximum flow of current is possible. Okay. And the voltage at anode and cathode will be, because this is just a conductor, just a wire, just a copper wire. So so if we connect a ohm meter from anode to cathode, if we connect an ohm meter from anode to cathode, it will be zero resistance ideally. And if it is the resistance is zero, then the voltage at anode and cathode is also zero. Three properties we have gone through now. One, if the diode is on, its resistance should be zero, voltage across anode and cathode will be zero, and there will be maximum flow of current. Okay? So if device is on, it exhibits zero resistance, zero voltage. Yes, if resistance is zero, voltage is zero, means it conducts large amount of current without any resistance. That is the ideal property of a diode. Okay, and if we draw the IV characteristic curve of this ideal diode when it is on, then the current is maximum, as said before. Short circuited, the current is maximum, so the current shown is maximum, and the voltage from anode to cathode is zero. We can see the voltage is zero. So if device is on, it exhibits zero. Okay, we have gone through already with this one. This is the on status of a diode. So we discussed about the ideal property of a diode. And because diode can have two state, it can be in the off state like any switch, and it can be in the on state like any switch. So the property of the diode when it is off, it looks like similar to the mechanical switch. The property of the diode when it is property of an ideal diode, remember, we should always use the word ideal. So property of the ideal diode when it is on, it looks like this mechanical switch. What more properties we have listed, I think maybe five or less, that these should be the property of an ideal diode. What more you think? One is when it is on, it has zero resistance, it has 0 volt. Second, 0 volt. Third, it can allow maximum flow of current without any barrier voltage, without any restriction, without any complications. It just like conductor, it should start the flow of the current. What more property we should look for in the ideal diode? Let's we discuss. uh, 6 is switch from off to on or vice versa instantaneously. That's correct. For example, if we, I mean, the time to turn it on and the time to turn it off should be very, very less, or should be zero. So no time delay, consequently no switching losses. So let's compare with the time delay. For example, this is a very fantastic and sophisticated piano switch. We need only the moment we press, it will turn on. Probably it looks like it will not take time. Okay, but if we compare this switch with this mechanical switch, this is a lever knife. This is the lever, and it's hang with some mechanical restrictions, so it cannot be pulled down without applying uh, a force. So it's probably, if we compare this switch with this switch, so we can say that this switch will take time to turn on from the off status, because we need to have push the power. If it is a very big, like the switches in the industries, so probably we need really, probably it will take, we need a very strong power to turn it on, and of course it will take more time. So comparing these switches, we can say that this switch will take less time and this switch will take more time. What about for the diode? Because we are studying the diode. So the sixth property of the diode should be that it should not take time. The moment we turn it on, it should turn on. The moment we turn it off, it should turn off. This is the this we assume in our design. So switch from off to on or from on to off instantaneously. So it should be without any consuming any time, ideally, but it's not possible. So the ideal things are not exist. So inconsequently, there will be no switching losses. For the ideal diode, there should be instantaneous turn on, there should be instantaneous turn off, and there should be no power losses when it is being turned on. There should be no power losses when it is being turned off. Okay, let's study some more property. What should be more? Hmm, let's Okay. Number seven is the seventh property, the ideal property for diode. Minimum power required to trigger switch on or off. Okay. The sixth was about the time, that it should not take much time, and the seven is to the power, because for this one, if we take with just a soft finger can turn it on immediately. Even a child applying very less power, it can turn on to off or off to on. But for probably for this one, yeah, we need more power. And for the ideal diode, we should think that take it should take zero amount of power to turn it on, or at least what we can say, the minimum amount of power. So the ideal diode should have this property, that when, if we want to turn it on, it should not take much, it should take minimum power, and when we want to turn off, again it should take minimum power. These are the ideal property of a diode. For example, uh, in the real diode, we know that we cannot turn it on immediately, like this one, instantaneously, and we cannot turn it on for the practical diode. We cannot turn it on instantaneously. It takes time, because the power has to reach to 0.7 volt, then it will turn on. And the power, and this for the practical diode, the power required at least is 0.7 volt in terms of the voltage. So we need both the time and the power to turn it on for the practical diode. So we study, normally when we design something, we try to uh, make its property close to the ideal property. So we should know the ideal and the ideal property, and we should know the practical property. So we should know that how much we are close to the ideal property. But Okay, what more property we should think yourself. Like, the easiest thing is that, okay, this 7 8, okay, it should be available free, no need to pay money. Okay, that's the ideal property. Yes, we think that we can have the human being, they can think that the ideal property of diode is, it should be that we should get always diode free, but we know. So this is the point where we can understand that the ideal is the human being idea. Human desires, but it's not possible. No one will give you free. Okay. So we studied something about the ideal property of a diode. You can rewind this video and maybe one time or two time you can understand, because this video uh, uh, is designed in such a way that if you pay attention, then you can easily understand all this material mentioned in this video. Hope we understand the ideal property of the diode. So now the time is review PN junction diode. We know already, but just we have a review. The topic we need to review. We should list down that topic. For example, what is this? PN junction are invented from a monocrystalline piece of silicon. Yes, the transfer of electrons from the n side of the junction to the p side of the holes diffuses, that produces a barrier voltage. This is, yes, we know about the barrier voltage. And PN semiconductor is a device that is called as diode. Yes, you know, if the external forward bias voltage is positive with respect to overcome the p junction barrier electric field, then diode turns on, allowing the flow of maximum current. This is about the forward bias. If the diode is forward bias, then the diode will turn on. Probably a reverse bias. If the diode is reverse bias, then there will be no flow of the current. Okay. And reverse bias p junction is show junctions show a temperature dependent reverse leakage current. This is less than microampere or nanoampere in a small silicon diode. So this is about the IS, that is the reverse saturation. If the diode is off, it will exhibit with the reverse saturation current. Okay, something graphically, the diode symbol and IV or VI characteristic along the x-axis. We have drawn the voltage. Probably the voltage is 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 5, 6, 7, 0 0.9, maybe 0. Maybe 1 volt, not more than 1 volt or 2 volt on the forward bias. So this region is where the anode is connected with the positive supply, and the diode starts to flow current. Then this region is known as forward forward region. And if the diode is supplied with the negative supply, that means anode is connected with the negative of the external supply, and the cathode is connected with the positive. So if the diode is reverse bias, then this is the region where the leakage current will exist. So reverse leakage current exists for this one, and in this case we say that the diode is in off status. Okay. For the ideal diode, the off status during the off status, the reverse leakage current should be 0. But for the practical diode, there exists leakage current that shows this, and this leakage current is in the range of nanoampere or the microampere. And the third region is this one, where we can see instantly a sharp flow of current starts through the diode. Although the diode is not forward bias, the diode is reverse bias. What we are doing here, the reverse voltage we are increasing, maybe -1 volt, -2, -3, -10, 20 minus 30 minus 40 minus 50 minus 60. Maybe we reach, if we keep try to to increase the reverse voltage, there will be a point where the diode will start, where the diode will completely turn on and the reverse current will flow, sharp reverse current will flow. So this region is known as avalanche breakdown. Remember, avalanche breakdown is the breakdown where if we exceed the reverse voltage beyond its capacity. Okay, so remember these three regions: forward region, reverse region, and the avalanche breakdown region. Hmm? Forward is only when the supply is positive, reverse and the breakdown is only when the supply is negatively connected with the anode and the cathode. The VI characteristic curve shown above is represented by the diode equation shown as this curve is represented by the, okay, for this one we have knee voltage 0.7. We assume that if this is the knee voltage, this is the 0.7 volt, and we can see that after 0.7 volt, maybe at 0.8 volt or 0.9 volt, there is a sharp start of current. So the current start, it means we say that the diode is short circuit. Diode is completely turned on here. After 0.7 volt, the diode is completely turned on because the maximum current starts to flow. Before 0.7 volt, we can say that, okay, if this is 0.7 volt, probably this will be 0.6 volt, 0.5 volt, maybe this is 0.1 volt, 0.2 volt. So we can say at this lower voltage than the 0.7 volt, the amount of current is very less. So it's ignorable. Try to focus on this curve and analyze yourself and ask yourself questions and get answered by yourself or by the PDF or the in this video or the from the textbook. You can get more answers. So this characteristic curve is governed by is by this equation. So this is known as the Shockley. I think he was the German engineer, the scientist. So he developed this one, and this is the Shockley equation. So this here we will study something more about. VD is the diode voltage, N is the constant, VT is the constant, IS is the saturation current, reverse saturation current, and ID is the diode current. We will study more in the next slide. Now, some numerical example: if a diode voltage is 0.1 volt, N is equal to 1, VT temperature constant is 24 voltage is uh, temperature voltage, I mean temperature voltage. VT is the thermal voltage constant, sorry, VT is the thermal voltage constant, and at room temperature I think it is calculated as 25.75 millivolt. So maybe it will change, but normally we, for the sake of simplicity, we take this value as a constant value. So the thermal voltage is constant here and the N is constant here. Diode voltage is given to you 0.1 volt. Find the diode current and state the region of the conduction if the saturation current is 0.1 microampere. So what is said, you can something get from this text that diode is plus is forward is plus 0.1 volt, which is plus. So it means the diode will be in the positive region, in the forward region, but it is not going to turn on because it is less than 0.7 volt. Let's start with this equation, Shockley equation, and then the ID is here. IS is given 0.1 milliamp microampere, and the diode voltage is 0.1 volt here. Exponential component is N is equal to 1 here, and thermal voltage constant is 25.75 millivolt here. So we can convert this into the milliamp millivolt to the volt and the minus 1. So if we calculate this one, we end up with this 4.79 microampere. Okay, and this is the answer. The question is over. But if we can approximate this equation, in this case we can see that the above equation can be approximated. Let's see, this part is 49 and this is just one. We can ignore this because this part is much less than this one. So what will happen if we try to approximate this one 0.1 and we make this one, and if we remove this term minus 1, if we make it 0, so what will happen if we calculate this one? The answer will be 5.79 microamps, and here is 4.79. So one, of course, 1 microampere is less, but this difference is not much as compared to the diode, as compared to the normal diode current. Normal diode current is maybe 10 milliampere, 20 milliampere, 100 milliampere, 1000 milliampere, more than this. So this current is basically, this is the diode current here, and this current is much more than the normal diode current. So we can say that okay, this and this can be the difference can be ignored, and we can see, therefore, for the case where id diode current is very greater than is, where is the is? Okay, the is, the reverse saturation current, is 0.1 microampere, and the diode current is yes, is 5, here is maybe it's 6 microampere. So as compared to 0.11 microampere means 100 nanoampere. So this condition valids here. For the case where id is much greater than is, the diode equation can be approximated as this. So we can approximate this one. We can ignore this part, second part, and we can say that okay, the diode equation is only this. So for the case if this condition is validated, then we can use the diode equation. You can replace this diode equation with this equation. Okay, we have to see the numerical example just we have gone through. Where is the operating point? The operating point, a voltage is, diode voltage is 0.1 volt, and the diode current is in the microampere, 4 or 5 microampere. We have to find out where is the operating point. So the diode voltage, forward voltage was 0.1, this is 0.3, maybe this is 0.15. So 0.1 is somewhere here somewhere, 0.1, and the diode current is not visible here. We calculated the diode current as 5 microamps or 6 microamps, but because this scale is in milliampere, 5 milliampere, so probably we cannot see this much smaller current here. So we can roughly we can say that the diode is off, although this is forward bias, but forward bias with 0.1 volt, but the diode is off and there is almost negligible flow of current. Okay, we can, so the operating point is this area. This area is the operating point, 0.1 volt. Okay. Next example, if a power diode has VD is equal to 1.2 volt and ID is equal to 300 amps. You have to go through this example by yourself, but just I want to point out the operating point for this example. Diode voltage is 1.2 volt and the diode current is 300 amperes, too much. So for this one, 1.2 volt is the diode voltage. This is 0.3.1 volt. We cannot even see here. So 1.2 maybe it's somewhere here, and if we sketch longer enough that we meet with this characteristic curve, probably at a very large distance we can meet, and of course then if we go upward, then the scale will change. not in the milliampere, but its scale will change into the ampere, and it's very at a very large distance, at a very far away point. Operating point is far away, where the vertical current is 300 amperes. So we will find that the operating voltage is far away, and at the operating point is at voltage 1.2 volt and the current at 300 amperes. We should have some visualization on the characteristic curve. What was the question? What is the answer? So you do it yourself. The important point is diode voltage is not 0.7, but it is more than 0.7. The diode will fully turn on, and the it can if it can have large amount of current. For this circuit, is a large amount of current is 300 ampere. So you do it yourself. Okay, the third region is the second region. So far we studied about the forward region. In the previous example, we took the example where the diode voltage was 0.1 volt, and in this case diode voltage was 1.2 volt. So both the example related with the forward bias. Now we see something about the reverse bias region. For the reverse bias region, if the applied voltage is negative, for the reverse bias region, diode voltage should be less than 0, means diode voltage should be negative on along the x-axis. Then the diode will be in the reverse bias region. Okay, we know. If diode, the example starts with if the diode voltage is minus 0.1 volt, so you can do it, and you can see that the if this exponential component is in the minus, so we can, if we calculate it, we can see that this is much less than the 1. So this can be ignored, and this simplified question will be simplified answer under this condition. When the diode voltage is minus, so the diode current will be minus saturation current. Okay. Third region is the breakdown region. We know if a diode is reverse bias, then it remains off and there is no flow of current through that diode. But so if the diode is reverse bias, we know the property of the diode. If the diode is reverse bias, then there is no flow of the current, diode remains off. But if we keep on continue to increase the diode reverse voltage, for example, initially we applied minus 1 volt, then minus 2, minus 3, and we have seen, so if we keep continue to increase the reverse voltage, what will happen? For example, if you applied minus 10, minus 20, minus 30, minus 40, there will be a point where the diode will turn on automatically. And this point, I think in this graph, the point might be is minus 55 volt. So the minus 55 volt will be set as a breakdown point, and under this breakdown point, the diode will completely turn on, and because the supply is in the negative, the current will start in the negative. This property is the breakdown region. We know if a diode is reverse biased, then it remains off and there is no flow of current through that diode. However, if the reverse voltage is further increased, minus 10 to minus 20, minus 20 to minus 30, further increase, and if we keep continue to increase, then at certain voltage, PN junction breaks, it will rupture. This high reverse voltage is known as breakdown voltage, and the region is known as breakdown region. So this region is the breakdown region, and this point here, minus 55 volt, it will be known as breakdown voltage. So this is the breakdown point. The breakdown voltage usually is very high compared to the forward voltage. It can be 10 volt, 100 volt, 1000 volt, or more. It depends on the material. It depends upon the size of the diode. If the diode is designed for very high voltage and very high current, then its breakdown point will be very high. If the diode is designed for very low voltage and very low current, then of course its breakdown will not be as high as this value. Okay. So this causes a sharp increase of reverse current flow. The operation in the breakdown region could be destructive if the large current is not limited by a resistor. So because the voltage is in the negative and the very high voltage, and the soon it turns on in the breakdown region, then there will be a maximum flow of the current. So we must have to put a high resistor in order to save this diode, otherwise this diode will burn out. So topics to be refreshed here: semiconductor material. These all topics you have to review. I'm not going to read it again and again. Now the assignment one is that you have to write notes on each of the topic, couple of sentences with graph and with figure. So the assignment one is part one. Write notes with illustrations and figures on the topic listed in the previous slide. So the previous slide topic on the previous slide, we have to write the notes on each topic. Number two, part two assignment one, part two, draw the forward characteristic curve VI curve of a diode using Shockley equations. So this is the Shockley equation, and you have to draw the graph, only the forward bias graph. So only you have to draw the forward bias graph. So it means that you should take different values of the diode voltage. First you can take 0, 0.1, 0.2, 0.3, 0.4, 5, 6, 7, 8, 9, 1. So for this one, take different values. Maybe you can take 10 values, maybe you can take 100 values. Use forward voltage from 0.01 to 1 volt, or you can also use, if you are drawing by hand, then you can use 0.1, 0.2, 0.3 up to 1 volt. But if you are drawing in some software or in Excel sheet, then it's better to use this resolution. So you have to take, for example, for 0.1, 0.01 volt, you have to calculate the diode current. For 0.02 volt, you have to calculate the diode current. So you have to make two columns, one column for the voltage from 0.1 to 1 volt, and the second column will be the calculated current for this voltage. So make two column, one column is for the voltage and second column is for the current, and the current you can determine from this equation. Take this constant value, is 10 microamps, Vt thermal voltage is 25 millivolt, and N is equal to 2. And you have to draw and then you have to send me, and you can find out, clearly point out in your graph where is the threshold voltage, at which voltage this this diode completely turn ons. Okay, so I think the class is over. I took more time here than usual. Okay, class is over. Thank you and Allah Hafiz.